First up on stage, we have Samantha Gangapersad, a master's student in Department of Civil Engineering under the supervision of Prof.Susan Gaskin and Professor Sidney Omelon, and she'll be presenting on engineering a circular phosphorus economy for sustainable food production.
Let me take you for a walk. And as we walk through this path, what strikes me is that nothing is wasted. Every leaf that falls to the ground decays, nutrients released, and then plants absorb those nutrients. Nature is perfectly circular. However, our economy is not. Today I'll be talking about our phosphorus economy, which looks like this. Every year, over 1 million tons of phosphate fertilizer is shipped to Canada, mined phosphate fertilizer, that is, and applied to agricultural fields. And then there is runoff from agricultural fields that goes into rivers and water bodies and contributes to eutrophication, and excessive growth of algae that is bad for biodiversity as well as quality of life. And also, you all play a role in this phosphorus economy. Whenever you buy food and you bring it to your homes with you, you cook, you eat, you go to the washroom, you produce waste that has a lot of phosphorus in it. And that waste can also contribute to pollution. However, we have wastewater treatment plants. Wastewater treatment plants treat the domestic sewage that comes from our homes. This is a picture of the Ottawa wastewater treatment plant. And at these plants, they precipitate phosphate so that the effluent that leaves would have less phosphate and would contribute less to eutrophication. At this plant, they add salts to precipitate the phosphate, and we have a lot of iron and aluminum phosphate in the biosolids. So this is at Ottawa, and the final solid product is called biosolids, consisting of this. Lots of insoluble iron and aluminum phosphate. So when I look at this linear economy, I see an opportunity for circularity, don't you? What if we take the insoluble iron and aluminum phosphate, make it soluble, and put it back to agricultural fields? That will allow us to create more circularity and use less mined phosphate. And this is where our research comes in. How can we take insoluble phosphate and make it soluble? So we plan to do this by taking elemental sulfur and adding elemental sulfur to biosolids with the insoluble iron and aluminum phosphate, and we react that at different temperatures, times, and molar ratio. What we expect to happen is for the microbes in the biosolids to convert this elemental sulfur to sulfide. The sulfide will then displace the phosphate, and we will have phosphate ions released that we can then use to make a bioavailable phosphorus fertilizer. This is our method, and so far we've seen that the method works. We release about 7% of phosphate, and we continue to work on it so that we can optimize and improve this. And if we can fill in this missing gap to having a more circular phosphorus economy. With this solution and many other circular economy solutions working in harmony together, this is how we can become more in sync with nature. And this is the only way for us to have a circular economy and a sustainable future.